Topic for Chapter 5 is energy expenditure, and the end of the chapter discusses possible mechanisms for fatigue. The chapter overview is a discussion of how to measure energy expenditure, both direct and indirect methods. Then it discusses what happens to energy expenditure as a result of exercise. And the final part of the chapter discusses potential causes of fatigue, both central nervous system, metabolic, and other causes. Measuring energy expenditure directly is somewhat difficult. You need to have a direct calorimeter, which is a room that's surrounded by a layer of water, and when you exercise in the room, it releases heat, and that heat eventually heats up the water around the room, and you can measure the change in temperature of the water as your direct measurement of the amount of heat that the individual put out as they did the exercise. So that would be a direct measurement of heat, but it's not very commonly done because of the expense and the need for a direct calorimetry setup. So you also need a technician, you also need a lab room, and so it's more difficult to do direct calorimetry. On slide 4, there's an artist rendition of a direct calorimeter. You'll see the person exercising, and then there's a room that is surrounded by a copper pipe that has water, and when the person exercises, the heat generated will be enough to increase the temperature of the water in the pipe, and that would be a direct measurement of the energy that the individual is putting out. But again, it's difficult. You need that whole setup, and if you don't have that setup, you can also do indirect methods of measuring energy expenditure called indirect calorimetry, and that's going to be based more on the amount of oxygen that is inspired and the amount of carbon dioxide that is expired. You can also do indirect calorimetry with equations, and I mean, at least in order to estimate like things like resting metabolic rate. So equations are typically the fastest and easiest way to do indirect measures. So mathematics is going to be part of this chapter, but not too much. So the pros on slide 5, the pros of direct calorimetry is that it's relatively accurate, and you're actually measuring what it is that you're supposed to be measuring. So it's valid. But like we said, the cons are it takes a lot of time, it's expensive, there's equipment that you need, there's people that you need to hire, there's lab space that you need to rent out. So it becomes somewhat impractical. Indirect calorimetry is going to be estimates of the amount of heat that you're spending based on the amount of oxygen and carbon dioxide that you're either utilizing or producing. It's a little bit faster. Obviously, it's much less expensive. So I think that when the time comes to get a very quick or a lab method of indirect calorimetry, especially in, say, for instance, Assumption College, where we don't have a direct calorimetry lab, I mean, we're kind of limited to the resources that we have. So energy expenditure based on these calculations is based a large amount on the amount of oxygen that you are breathing in. So VO2, the little dot on top of the V, refers to the amount of oxygen per minute. The dot means per minute. VO2 is the amount of oxygen that you're breathing in minus the volume of oxygen that you're breathing out. And that's going to be an indicator of the amount of oxygen that you're using when the oxygen is in your lungs. Also going to measure the amount of carbon dioxide that you're exhaling, which is the amount of carbon dioxide that's produced each minute. That's also V with a dot over it, CO2. It's the amount of expired carbon dioxide minus the volume of inspired oxygen, carbon dioxide, which is an indicator of how much carbon dioxide that you are generating during exercise. Figure 5.2a will show an indirect calorimetry method using direct capture of oxygen. you'll see that there's a treadmill, and the guy's probably doing a Bruce treadmill protocol. Although there are other protocols, exercise protocols that you can use to do direct capture of O2 and VO2, such as a Bruce treadmill bike test or any other really maximal exercise test. You'll notice that the person on the treadmill has a mask on, and the mask on has a one-way valve that allows oxygen and ambient air to come into the valve, and then the valve will close, and the ambient air will be exhaled out that tube, and that tube goes directly to a computer, and the computer can analyze the amount of oxygen and carbon dioxide relatively accurately. The person on the treadmill also will have like a nose clip to make sure that no air that they're breathing in or breathing out is not detectable. So um, the person on the computer will see variables like blood pressure, not blood pressure, heart rate, respiratory exchange ratio, and we'll get into what a respiratory exchange ratio is, and they'll monitor the each of the stages of the graded exercise test, and they'll monitor specifically respiratory exchange ratio, because when the respiratory exchange ratio gets higher than 1, specifically closer to like 1.1, 1.2, it's an indicator that the person has actually reached VO2 max. Um, on slide 9, the Haldane transformation is a way of mathematically representing the relationship between inspired oxygen and expired carbon dioxide. Um, I'm not going to ask you to do that mathematics. Oftentimes, the computer will have an algorithm that will take care of that for you. So as long as we are aware of using and how to use the oxygen cart, I'm not going to hold you to that equation. On slide 10, the respiratory exchange ratio is an important variable in these measurements, because number one, it can tell you when the substrate that is utilized for energy has changed. So in the beginning, your body will not be using as much glucose because it's not in glycolysis, and it'll be using more fat stores, especially as the onset of exercises, and you're still in the very, very beginnings of anaerobic glycolysis. There's not going to be much glucose that's used for fuel yet. So because of that, there's a change in the amount of oxygen that's needed in order to combust, in order to utilize the glucose for fuel, compared to something like a free fatty acid like palmitic acid. Palmitic acid is C16H32O2. Let's see the next slide. Yep, and on the next slide, slide 11, it will show you the chemical reaction that occurs when you break down one molecule of glucose. That has a respiratory exchange ratio of 1.0. It's because if you look at the equation, it says 6O2 plus C6H12O6 yields 6 carbon dioxide plus 6 waters plus 32 ATP. So if you take a look at the volume or the amount of oxygen that's utilized, which is 6O2, and you divide that by the amount of if you take the amount of carbon dioxide that is generated and you divide that by the amount of oxygen that is utilized, you'll see that there's a 6 CO2 divided by 6 O2. 6 divided by 6 is 1. So if the body is burning straight glucose, the respiratory exchange ratio is going to be 1. But you'll notice that the equation for palmitic acid is slightly different. It says 23 O2, 23 units of oxygen is needed to break down palmitic acid to 16 carbon dioxides, 16 waters, and 129 ATP. So what's really good is that with a free fatty acid like palmitic acid, you're generating 129 ATP as opposed to 32 ATP for one molecule of glucose. But with any fatty acid, or especially palmitic acid here, you see that there's 23 oxygen needed. So you need more oxygen to break down or to combust or to burn the palmitic acid. That means the respiratory exchange ratio is going to be a little bit different. It's a VCO2. In this case, it's 16 CO2. Divide that by 23 oxygen needed. And since oxygen is in the denominator, if the amount of oxygen needed to burn a particular fuel source increases, the respiratory exchange ratio is going to decrease. So, as an individual is running on a treadmill, they're going to start with a respiratory exchange ratio closer to 0.78. Then, as they run for a longer and longer amount of time, and the body goes into glycolysis and eventually straight into aerobic glycolysis, and it's burning straight glucose, you'll notice that the respiratory exchange ratio is going to start to slowly increase from about 0.78 to 1.0. When the RER gets to about 1.0, you know then that they're pretty much in the throes of slow glycolysis. And then eventually the respiratory exchange ratio is going to go so high that you can even use that as an indicator for potentially that they've reached their VO2 max. Because if the respiratory exchange ratio is higher than 1, it means they're generating or creating more carbon dioxide than they're able to bring in oxygen. So if they can't bring in oxygen any more to a greater extent, and they keep getting rid of carbon dioxide, it's an indicator that they've actually reached their potential VO2 peak or VO2 max. So respiratory exchange ratio is a value that you will come across on table 5.1. It shows the respiratory exchange ratio of burning particular fuels, right? Where fats, the respiratory exchange ratio is going to be a little bit lower, again, because of the increased need for oxygen to burn and to combust that fuel. And actually, rather than saying combust, I should say oxidize. But at the same time, I mean, oxidation seems to be a very similar process to combustion in terms of it seems like there's just the fuel source is burned up, just like gasoline would be combusted. Seems like food sources are oxidized. So I apologize if I use those terms interchangeably, but seems to be a pretty interesting similarity there. Carbohydrates, if you're burning straight carbohydrates, your respiratory exchange ratio, because of the contribution to oxygen in regards to the breakdown of glucose, is going to be relatively even. 6 units of oxygen to break down 6 units to create 6 units of carbon dioxide if the fuel is glucose. Therefore, the respiratory exchange ratio of 1. A couple of limitations to indirect calorimetry. Carbon dioxide production might not be the same as carbon dioxide exhalation. Respiratory exchange ratio is inaccurate because it does not account for protein oxidation. But because protein oxidation, or the utilization for protein as a fuel, is usually less than about 5% of the overall fuel resources utilized, oftentimes the protein contribution is ignored. Okay, so there's also if gluconeogenesis is occurring, because gluconeogenesis is usually occurring with a combination of free fatty acid oxidation. Oftentimes, the fact that gluconeogenesis is occurring at the same time as the fat-free acid oxidation, it can skew the respiratory exchange ratio associated with fat-free oxidation, because you're also breaking down sugars at the same time. There's a way of putting a particular isotope in water, and the isotope breaks down in a particular amount of time. And it's called doubly labeled water, where there's a carbon isotope and a hydrogen isotope, and you drink the isotope and it breaks down over a period of time, but we're not going to hold you to that in terms of on the exam or anything, but there are other ways of indirectly measuring energy expenditure. When the body is exercising, the metabolic rate is going to increase. At rest, the respiratory exchange ratio is a little bit higher or lower than 0.8, and the individual is usually using about 3.5 liters per kilogram per minute of oxygen. That's the generally accepted average VO2 max at rest for the population. And for the most part, individuals are burning about 2,000 kilocalories per day. Metabolic rate is associated with the amount of energy that you're expending at rest, or during exercise. But in this case, the basal metabolic rate is the amount of energy that you're expending at rest. Somewhat difficult to measure. The individual has to be laying down. They have to have had at least 8 hours of sleep and 12 hours fasting, and they go into this basal metabolic rate measuring chamber, and they have to stay relatively motionless for a large amount of time, and it becomes somewhat time constraining and somewhat of a difficult measurement. So we don't really utilize basal metabolic rate too much. We actually use resting metabolic rate. We're on slide 17. Resting metabolic rate is similar. It's only about 5 to 10% different, but it's much easier to calculate, and normal values for resting metabolic rate are going to be between about 1200 to 2400 kilocalories per day. That means that your body needs a particular amount of energy just to be alive. As when you're alive, your heart is beating and your eyes are blinking and you have circadian rhythms in your eyes and your brain is thinking. And so in order for all of those activities to occur, your body needs at least 1200 to 2400 kilocalories per day. If you don't eat that much calories, that many calories, then your body is going to have to get the calories from somewhere else, and the somewhere else that the body is going to get calories from is either the gluconeogenesis or glycogenolysis, or if you have so little muscle and liver glycogen that you cannot go through an appreciable amount of gluconeogenesis or utilization of sugar stores for fuel, then your body's going to have to resort to using fat. And if it needs to, it's going to start using your fat-free mass, your muscle mass. And that's not what you want, because the more you use your muscle mass, the less your body is going to be able to functionally perform those those activities of daily living and functions that you need to survive. So you definitely don't want to be eating your fat-free mass for fuel. Total daily metabolic activities includes all of the activities aside from your basal metabolic rate, such as the thermodynamic effects of eating. When you eat food, your stomach churns and your intestines move, and peristalsis happens, and there are chemical processes that break down the macronutrients, and that all costs energy. The amount of energy that people expend during those eating processes, combined with the amount of energy that is spent with regular everyday activities like walking, talking, taking a shower, going to work, doing any of the activities you do like sports or sewing or gardening or anything like that, those are part of your energy expenditure for the day as well. So you have three things contributing to the total amount of energy out: your resting metabolic rate, your thermodynamic effects of food, and your total energy expenditure for all other activities. Normal ranges for total daily metabolic activity is about 1,800 to 3,000 kilocalories per day. If you look at any of the food labels, the food labels are designed after a 2,000 kilocalorie per day average energy expenditure for the typical height and weight of a U.S. adult. Competitive athletes are closer potentially to as high as 10,000 kilocalories per day. If I do health-calc.org and I put in the criteria of workout and age and all that stuff for my athletes at the gym, they're typically 3,000 to 4,000 calories per day, especially the older guys. The older guys are at 3,800 to 4,000 kilocalories per day. As exercise intensity increases, metabolic rate also increases. Typically at higher outputs, the VO2 is going to continue to increase, and there's also going to be a recruitment of more type 2 muscle fiber types. And type 2 muscle fiber types are fast twitch power muscles that have less oxygenation and less mitochondria. And so because of that, there's more of a reduction in the efficiency of the utilization of oxygen as the exercise intensity increases, because of the turnover from type 1 predominantly to type 1 and type 2 muscle fiber types. You'll notice on slide 19, figure 5.3a, they have an individual in purple biking at 50 watts for, says 2 minutes there. And you'll notice that after about 2 minutes, the oxygen